So in this problem, here's a chain and a rope, and I just hands under its weight from two support. So because of the weight on the chain or this rope will just naturally curve down, right? This curve we call it catenary. So now I want to derive the equation of this curve. And our goal is really to find out the, let's say this is y, this is x. So what we are really looking for is a relationship between y and x. Okay, so how do we start that? Again, because it's a continuous system and it's not moving, so I'm going to slice, just focus on a little piece of my system and then draw the free body diagram and then do F equals ma. So let's see. So this is my rope. I just focus on this little part. And on this little part, I can see I have a tension pulling this way. I have another tension pulling this way. Of course, that these two tension will be different. This will be the tension at x. This will be the tension at x plus dx. And then this one also feel the weight going down, right? Okay, so if I choose this is my x, this is my y, now I can break it into x direction and y direction. So in the x direction, of course that I can, put in the angle here. I can say, oh, there's an angle here, there's another angle here, and try to decompose it. But I don't want to do it right now because I already have x and y, and adding up another theta here seems not a wise choice. So I will try not to do it unless I have to do it later. Okay, so here I realize that this in x direction, the tension, the x component of the tension here and the x component of the tension here, they should be the same because they are balanced. In y direction, I can tell that y component of this tension should equal to y component of this tension plus the gravitational force. So this is lambda times ds times g. This is the mass, while ds is just the length of this little segment. That's dx squared plus dy squared. And take the square root, which is this. Okay. And then once I have that, I will keep moving on and see what I learned from that. So from the x component, I learned that the tension in x direction is constant. So it depends on how tightly or how strong that the two supports are pulling your rope. In the y direction, we see this. Okay, and then again, I can isolate I can take a dx out of my square root and then do a little bit math trick here. So I'll leave it to you to try to follow all the little steps. And then anyhow, in the y direction, I eventually come up with this. So this equation, because our goal is to find the XY relationship, this one seems this two information doesn't seem very useful. Because it will be useful only if we can somehow engineer this two to come up with a differential equation that's related to dy and dx. So how can we do the connection? How do we connect the dy dx to txty? Then actually we notice that the tension is always at the tangential line of the rope, right? So so this tension, the dy dx, which is the direction of the tension, that should be which should be the same as the slope of my rope. That's dy dx. So now I can try to manipulate this two equation and come up with this, and come up with a dy dx differential equation and solve for that. Okay. All right. So there's a very key connection here. But essentially, I think I really want you to practice is to isolate one and, one segment, and then you can draw the free body diagram well.